Okay, so what we're going to do today is sort of finish up the reactivity of the alcohol. So we've already spent a fair amount of time discussing how we can prepare alcohols from a variety of different starting materials, as well as react them to form alkenes, to form alkyl halides. Alright, and we're going to continue today with the reactions of alcohols to give us, in this case, esters or carbonyls or protected alcohols. So 3 different reactions that we're going to talk about in this online lecture. Okay, the first one here is going to be, again, we're going to talk about reacting alcohols to make esters. In an esterification reaction, we're going to talk about alcohol oxidation, and then we'll talk about alcohol protection. Alright, so in the first case, the forming esters, that's what I've shown up here on the first part of this chemdra. But what I'm showing here is that I can take benzoic acid and react it with methanol under under acid conditions, and a fair amount of heat I can generate the methyl ester directly. So this product over here, it turns out that you can do this reaction, but it requires some reasonably harsh forcing conditions. So the better option in many cases is to go through this intermediate here, this acid chloride. Okay, so I'll make the acid chloride using this thionyl chloride, this SOCl2. Use that to make the acid chloride, and once I make that acid chloride, that is substantially more reactive and will easily react to generate the methyl ester. We're going to postpone any kind of detailed discussion of this mechanism until we get to the carbonyl chapter, and then we're going to talk about it quite a bit. But that's the overall esterification reaction. So again, I can use alcohols, combine them with carbonyl groups, either the acid chloride or the carboxylic acid directly, and generate esters. Another reaction of alcohols, and this is the second reaction we're going to talk about today, is the oxidation of the alcohols to give carbonyl compounds. And this is actually an extremely useful and widely used reaction. So we're going to take some time to make sure to go through it carefully. If I start with in this case, a primary alcohol, I can oxidize that primary alcohol to give me an aldehyde compound. And if I further oxidize it, if we view oxidizing just sort of roughly speaking as adding more oxygens, I can oxidize it even further to form this carboxylic acid shown over here. So again, primary alcohol can oxidize to aldehyde or all the way up to carboxylic acid. Secondary alcohol, which is the second line here, can oxidize up to a ketone if I oxidize it. And the third line, this tertiary alcohol, so again, if I have an alcohol that has 3 different substituents attached to it, and I try to oxidize that, in that case I'm going to get no reaction. And the reason that tertiary alcohols are inert to oxidation attempts is that if I want to form a carbonyl compound from this starting material, that's going to require me to break a carbon-carbon bond, some kind of CC bond here to get that carbonyl, and that's a pretty difficult reaction. So under the context of these oxidation conditions, tertiary alcohols do not react. But again, a primary alcohol can give me an aldehyde or a carboxylic acid, and a secondary alcohol in this case can give me a carbonyl compound, a ketone shown here. As far as what reagents and oxidants do I use to get this to react, here I have a number of choices. So I can use a number of reactants shown over here. These oxidants here, this is potassium permanganate, KMNO4, or I can also use chromium trioxide, CrO3, or this other high oxidation state chromium compound, Na2Cr2O7. Okay, and these are really good for, let's see, going from a ketone to from a secondary alcohol to a ketone, and also going from a, so these are great at secondary alcohol to ketone, and they are also great at primary alcohol to carboxylic acid. Okay, any of these choices of oxidants, this manganese, the KMnO4, CrO3, and this Na2Cr2O7, these can all do the secondary alcohol to ketone oxidation. They can also do the primary alcohol to carboxylic acid oxidation. For these reactions, the primary alcohol reactions under these conditions, aldehydes form as intermediates in the oxidations. Okay, so you don't go directly from primary alcohol up to acid. You do go through this aldehyde intermediate. However, the aldehyde intermediate is so reactive under these conditions that it is virtually impossible to isolate that aldehyde, and instead these go all the way up to the carboxylic acid. Now, what are my options if I want to stop at the aldehyde? Well, then I really can't use any of these kinds of metallic, metal-containing oxidants. Instead, I have another choice here. This is called Des-Martin periodinate, or DMP for short. Okay, so I'm just going to abbreviate that as DMP. And this is the structure of the DMP. And what this reagent is it's not, the cheapest reagent by any means, but it is great at doing the mild oxidation of primary alcohol to aldehyde. Primary alcohol to aldehyde. Now I have a number of other, I can also use DMP to get a secondary alcohol to ketone. However, because it is a fairly expensive reagent, in most cases what I do in that, for the ketone formation, I use one of these oxidants, and only in the case where I want to do primary alcohol to aldehyde do I use my DMP to affect milder oxidation conditions that allow me to stop at the aldehyde. So that's what I mean when we talk about alcohol oxidation. It can start with a primary or a secondary alcohol, and depending on the choice of oxidant that you use, form an aldehyde, form a ketone, or form the carboxylic acid. Now, the third reaction I would like to discuss today is the reaction of, or the protection of alcohol. So, alcohols have a proton that is somewhat labile, so it can come on and off without too much difficulty. And that kind of proton tends to interfere with a number of potential reactions that we may want to affect. And I'm just showing one example here. If I want to start with this bromo alcohol and form a Grignard reagent from there, my normal formation of a Grignard reagent is to treat that alkyl bromide with magnesium and ether. So if I just focus in sort of on this half of the molecule, I could say, okay, I have alkyl bromide, let me just add magnesium metal, I'll form this, life will be good. But it turns out that this doesn't form. And the reason this doesn't form is because the alcohol is an incompatible functional group. Okay, so that what I mean by that is I can form that Grignard reagent, and it's immediately going to react with the mildly acidic proton on the OH group. That mildly acidic OH group is going to form the hydrocarbon alkane from this Grignard. So if I form that Grignard, it will immediately then reduce to the corresponding alkane as a result. So if I do actually want to form this Grignard reagent in this context, what I need to do is protect the OH group as something that's not going to interfere with the reaction, then do whatever kind of reactions I want, and then when I'm done with those reactions, I deprotect that protecting group and end up back with my desired OH. Okay, so this is a three-step solution. In the case where I have incompatible functional groups, I can protect in some way, then do whatever reactions I would like, and then do a deprotection at the end of the reaction when I'm done with that activity. Alright, and there are a number of possible protecting groups for alcohol, so I'm just going to go through one of the most common classes, and that is silicon protecting groups. Alright, so a silicon protecting group is a silane kind of thing. And this compound over here that I'm showing is TMS, that's trimethyl silochloride, or I can abbreviate that as TMS chloride. And this trimethyl silochloride if I react that with an alcohol, an OH group, and a base like triethylamine, that triethylamine will pull off this hydrogen, use the oxygen to attack the silicon, kick off the chloride, an SN2 type reaction. And what I form from there now is this OTMS, this protected alcohol version. I abbreviate that as OTMS. That's an oxygen bound to a silicon with the 3 methyl groups. Alright. And this compound, this protected alcohol, turns out to be inert to all kinds of reactions. So if I had other stuff going on in the rest of this molecule, it would be really easy for me to go ahead and get that molecule to react. Now, if you're thinking to yourself, and I mentioned that this is an SN2 type mechanism, if you're thinking to yourself that SN2 mechanisms do not happen, reactions do not happen on tertiary carbons, that's correct. Alright, they do, however, happen on tertiary, or these highly substituted silanes. Alright, so again, if this were a chloride, this were terbutyl chloride, this wouldn't react at all. Alright, but because it's a silicon instead, this turns out to be a very easy reaction. And the reason for that is that the carbon-silicon bond is substantially longer than the carbon-carbon bond. And as a result, you have much less steric crowding around this silicon center, again, because these methyl groups, instead of being right up close to the silicon, are actually spread further back. And that enables my alcohol, my nucleophilic alcohol, to come in and do the SN2 type attack on the silicon and kick off the chloride without being bothered too much by the steric interference around the silicon center. And then again, I can do whichever reactions I want, and when I'm done with the reactions, I can deprotect my protected alcohol by treating this silyl ether, that's what it's called the silyl ether, so let's write that here, with either aqueous acid or most commonly fluoride, alright, some kind of fluoride ion source. So for example, TBAF is a good one, that's tetrabutyl ammonium fluoride, to regenerate the OH alcohol, and then the silicon silanol as my side product here. Most commonly we use F- for deprotection, and the reason for that is that the F- does not react with any other parts of the molecule, whereas the aqueous acid may or may not be a potentially interfering with other parts of my molecule again. So I can protect the alcohol by reacting it with TMS chloride and the presence of a triethylamine. I can react whatever I want, and then when I'm all done with my reaction, I can do deprotection as my third step, treating it, for example, with TBAF to reform the alcohol and the silanol product. So that concludes all of the reactivity of the alcohols discussed in Chapter 17. We will continue after spring break with a discussion of phenols. So those are the OHs directly attached to a benzene ring, and the reactivities and how the reactivity of the phenols differs in these cases.